Alright, so to build this physics project, we had two options. Either do preliminary calculations or just build it and hoped it worked. So we kind of did like a mixture of the two because we did have some other sources before we actually built the project, but we didn't do any actual calculations. So in order to build this project, we looked at online sources to see what other people had done, and we took that into account. And we also consulted past physics students to see if they had any advice about building the actual project. So a lot of people we talked to said that we should use something to create tension. So we decided to use springs. So we have three different springs here. We have two big ones and then one smaller sized one. So when we first attach the springs to the apparatus, we put all three on, and we learned that made the ball launch way too far. So then we tried just one big spring, and that didn't launch far enough. So then finally we put the two big springs, and that launches about almost exactly 20 meters. The next thing to think about was the angle that the catapult actually launches. So we know from physics that a ball or a projectile goes the furthest when it is launched at a 45-degree angle to the horizontal. And so we wanted to try to replicate that in our apparatus. So as you can see here, we have part of a pipe, and it's attached to the arm. And these holes in the side of the apparatus, the pipe can be moved depending on what angle you want. And so we moved it a few different times to see what would work best. And actually, for this particular apparatus, it doesn't launch at a 45-degree angle because that made it go way too far, even with adjusting the different springs. So when it is actually launched, it's launched at about a 30-degree angle.
We ran 3 trials with the same 2 springs every time. We didn't use the third smaller string for any of our 3 trials. And we used the same standard ball for all of our measurements for these 3 trials. And so what we did was launch the apparatus. We had one group member stand about 20 meters away, and we launched it, and the same group member started the time when we launched it and then stopped the time when he saw the ball fall. So we knew how long it would take for the apparatus to launch and for the ball to drop. And then we measured from where the ball dropped to where the apparatus was, and we did this 3 times to ensure accuracy and to get a good average. And then to measure the angle, we took a protractor and we measured from the horizontal, and using that we found that it was about 25 degrees from the horizontal, and that was the angle of our projectile.
Okay, so this is the data table for our measurements. So first we have the apparatus height of 0.305 meters. So that's where the height of where the ball was launched from. Next we have the horizontal displacement of 21.4884 meters. So that's the distance the ball traveled from the catapult. Then we have the time. So we measured the time it would take from the ball to when it started to hit the ground. And we did 3 trials, so it was 1.66, 2.025, and 0.8205 seconds, which averaged out to be 1.50 seconds. And finally, our angle of launch was 64.29 degrees from the vertical. So what does it mean from the vertical? So here is a diagram of what that meant. So over here, this is where the ball launches from, and this right here is the catapult arm. So we measured the angle from the horizontal there, which was 25.71 degrees, and then we drew a triangle from where the ball launched. So as here is the vertical, and then so here would be the 25.71 degrees, and then this is the 64.29 degrees as you subtract from 90 degrees. And this is what the angle we used for our calculations, as you can see here. This is the 64.29 degrees, and here is the Vy, and here is the Vx that we can use to calculate the horizontal and vertical velocities.
Alright, so for this project, we had to calculate the horizontal velocity, or the x velocity, the vertical velocity, or the y velocity, and finally the resultant velocity, which is the velocity that the ball is actually launched at. And so we knew the angle that the ball is launched at based on our measurements, and so knowing that angle, we can draw a right triangle. And so if you see our frame of reference, the ball is launched at 64.29 degrees to the vertical. And so the vertical is like the y velocity, and the horizontal is the x velocity. And so this is the resultant of where the ball is launched. And so we can break this up into an x and y component. And so in order to do this, we first had to calculate the x velocity. And so we knew the horizontal displacement of the ball based on our measurements, and we also knew the time, which we averaged based on our measurements. And so velocity is equal to displacement over time. And so the velocity of the x direction is equal to 21.4884 meters over 1.50 seconds. So then we calculate that, and we see that the x velocity is 14.3256 meters per second. So now that we know the x velocity, we can also find the y velocity using SOHCAHTOA, which are properties of right triangles. And so based on this triangle, we know that tangent of 64.29 degrees should be equal to the x velocity over the y velocity. So tangent theta is equal to opposite over adjacent. So tangent of 64.29 degrees is equal to the x velocity, 14.3256 meters per second, over the initial y velocity. Once we calculate that, we see that the initial y velocity is 6.89752534 meters per second. And this is only the initial y velocity, because the x velocity is not going to change, as there's no force acting upon the horizontal motion. However, gravity is acting upon the vertical motion, as gravity is going to make the ball slow down as it goes up, and speed up as it travels back down to Earth. And so this is only the initial y velocity. So now that we know the initial y velocity and the x velocity, we can calculate the resultant velocity using a squared plus b squared is equal to c squared. So once we plug in the vx for a and vy initial for b, we can calculate the resultant velocity, which is 15.89964375 meters per second.
So since we used longer numbers during our calculations to ensure accuracy, we filed them down for our final answer. So our horizontal velocity is 14.3 meters per second. Our initial vertical velocity is 6.9 meters per second, and our resultant velocity is 15.9 meters per second, and these are all with correct sig figs, which would be 3 sig figs, which we based off of our time originally. Okay, so after we finished doing all our calculations for this project, we were curious about what the maximum height the projectile traveled after it was launched. So to figure this out, we used our initial y velocity, which we had through our calculations we already known that, but we can recalculate it because we know that the velocity at the topmost point is going to be 0. And you can use that to solve and find for the initial velocity. And then we knew what the time was already for the entire projectile. So if we divided that in half, we would find how long it took for the projectile to go from the ground to the topmost point. And then we knew what our theta value was. And so we used all of this and we plugged it into equations.
Okay, so to solve for the height, so we use distance of acceleration equals velocity initial times time plus 1/2 times acceleration times time squared. So we know the initial velocity is 6.89752534 meters per second, and we know the time right here is 0.750 seconds, and then plus 1/2 times negative 9.8, then times 0.750 seconds squared. And we know it's negative 9.8 because, as we defined here in our reference frame, the up direction is positive, so the down direction would be negative. So then it would end up being distance acceleration is 2.41369409 meters, but we also calculated this from where the ball was launched. So So we have to add in the initial height of the catapult, which was 0.305 meters. So then the final answer is 2.721894009 meters. And with sig figs, this ends up being 2.72 meters from the ground.